Hello, learners. Let me begin with a fun thought. What if you walked into a chemist's shop and asked for a medicine, but instead of its proper name, you just said, "Give me that tasting thing," or "the one from lemons"? Total chaos, right? That's exactly why organic chemists needed a systematic way to name compounds. You see, in the early days, we called things based on their origin, like formic acid from the Latin word formica, meaning ant, because it was first isolated from red ants, or citric acid from citrus fruits. But imagine trying to remember millions of such names, a nightmare. That's why the International Union of Pure and Applied Chemistry, or IUPAC, stepped in to give us a structured naming system. Today, whenever we say a name like ethanol, every chemist in the world knows we mean the compound with a chain of 2 carbons and a hydroxyl group. That's the power of systematic nomenclature, clarity, precision, and universality. Now, let's get into the core of IUPAC rules. The very first step in naming an organic compound is to identify the parent hydrocarbon chain. That's the backbone. If it is fully saturated with only single bonds, we add the suffix ane. So CH4 is methane, C2H6 is ethane, and C3H8 is propane. If a double bond is present, we use Na, such as C2H4, which is ethene. A triple bond uses yane, like C2H2, which is ethine. Each name begins with a prefix showing the number of carbons, meth for 1, eth for 2, prop for 3, but remember the first 4 are taken from traditional roots. Beyond that, it is systematic. Think of it like postal addresses. You cannot locate a house without knowing its street and number. Similarly, chemists cannot locate a molecule in the chemical universe without its parent chain. Alright, suppose your molecule is not a simple straight chain but has branches, like a tree sprouting twigs. The longest continuous chain becomes the parent. The smaller groups branching out are called alkyl substituents. Each carbon in the main chain is numbered in such a way that substituents get the lowest possible numbers. For example, in a chain of 9 carbons with a branch at carbon number 2 and another at carbon number 6, the correct name is 6-ethylmethionine. If you numbered it the other way, you would get higher numbers, which is incorrect. When multiple identical substituents appear, we do not repeat the word every time. We use prefixes like di for 2, tri for 3, or tetra for 4. So if 2 methyl groups are on carbons 2 and 4, the name is 2,4-dimethylpentane. And always remember, substituents are listed alphabetically, ethyl before methyl, ignoring those di and tri prefixes. Once you get used to this, naming becomes as fun as solving crossword puzzles with carbon atoms. Now let's bring in the celebrities of organic chemistry, functional groups. They decide how a compound reacts, and each has its own suffix. There is also a strict order of priority. At the very top is the carboxylic acid group, written as -COH. Next comes sulfonic acid, then esters, acid chlorides, amides, cyanides, aldehydes, ketones, alcohols, amines, and finally the carbon-carbon double and triple bonds. The rule is simple. Number the chain from the end that gives the principal functional group the lowest possible number. For instance, if both a hydroxyl group and a keto group are present, the keto group takes priority and the alcohol is named as a hydroxy substituent. Think of it like a red carpet event. No matter where others stand, the carboxylic acid always walks first. And yes, forgetting this priority list is one of the most common student mistakes, so keep it handy. Let's practice with a solved example. Consider the compound HOCH2-CH2-CH2-CH2-CO-CH3. Step 1. Find the longest chain including the carbonyl group. That gives us 7 carbons, so the parent is heptane. Step 2. The carbonyl group, that is the C double bond O, is at position 2, so we call it heptentuvin. Step 3. There is also a hydroxyl group at carbon number 7, so we add hydroxy as a prefix. Put this together and we get 7-hydroxyheptentuvin. Every locant and every prefix counts. Without these rules, one could call it hydroxyheptanone, vague and misleading. With IUPAC rules, it is precise like a chemical passport. Next, let us enter the aromatic world, benzene and its derivatives. The parent name is always benzene and substituents are written as prefixes. A methyl group gives methylbenzene, commonly called toluene. A nitro group makes nitrobenzene. If two substituents are attached, numbering decides their names. If they are at carbons 1 and 2, we call it 1, to the substituted benzene or simply ortho. If they are at positions 1 and 3, that is meta. Positions 1 and 4 are para. For example, 1,3-dibromobenzene is a meta isomer. When there are more than two substituents, ortho, meta, and para cannot be used, and we follow the lowest locant rule strictly. So the correct name is 1-chloro-2,4-dinitrobenzene, not 4-chlorovan,3-dinitrobenzene. And when benzene acts as a side group attached to a larger chain, it is named phenyl. That fragrant word, phenyl, in perfumes is simply benzene acting as a stylish accessory. Let us wrap up. The IUPAC system is the universal language of organic chemistry. First, identify the parent chain. Next, find the functional group. Then assign numbers carefully to give the lowest locants. Add substituents in alphabetical order. Finally, use the right suffix. Whether you are naming a simple hydrocarbon, a branched alkane, or a complex polyfunctional compound, these rules ensure universal clarity. In real life, this is vital. Drug companies rely on exact names to patent medicines, industries use it for fuels and polymers, and biochemists use it to describe molecules in our cells. Once you master this, you can look at names like 2,3-dimethylbutane or 3-nitrocyclohexane and sketch their structures instantly. Isn't that like Google Maps for molecules? So remember, nomenclature is not just memorization, it is a precise navigation system for chemistry. I hope today's session made this naming game both logical and fun. Until next class, keep decoding molecules with confidence.